Hi, it's Terry Dennery of the MathWorks. So I did a guest lecture yesterday for a local university, and it's kind of a long session. I think I'm going to be able to bring this one in under an hour. But anyways, I kind of like the content, and and it's stuff I've talked a lot about, and I've recorded and put into videos before. But it's kind of a nice packaging. I thought it kind of went well together. All right, and so we're going to kind of get to this. It's a mechanical linkage. You could call it a pendulum. It basically has a pinned connection right here. Otherwise, it's a bar that will move according to gravity as well as a torque. Right-hand rule, kind of rotating that way. Okay, so anyways, and the lecture kind of was following up on stuff on DC motors. So we're going to begin with kind of the DC motor, right? And again, lots of videos of me doing DC motors. I'll essentially kind of describe the solution that there's an electric circuit with an inductor, a resistor, and essentially this back EMF generator, I'll call it, all in, one, what do they call it, one series or branch, of circuitry that's connected, with the voltage source. And the basic idea is that the applied voltage will be balanced by the voltage across the inductor, the resistor, and then the back EMF piece coming right there. Okay, and again, there are lots of videos kind of where I derive this, kind of show where this comes from, and hopefully what I'm doing makes pretty good sense. And I think I won't just go too much further than that, other than to point this out. All right, what is this? Well, that's the mechanical load for a motor that's just going to turn its own shaft, which makes the inertia of the shaft one of the key parameters. But in reality, nobody cares about the inertia of the shaft because it's really what it will be connected to, which is the most relevant thing. So anyways, probably lots of people have tools like the ones I demonstrate. We'll demonstrate on a DC motor, but in a way it's a very kind of, I'd say, unimportant problem. And a much more important problem, could be something like this, and the idea of controlling the angle of a linkage and maybe even a more complex mechanism. Certainly, you see this in all kinds of things, and I won't try too hard to justify that either. But let's kind of continue with this idea. All right. And so the other thing, we parameterize this, and essentially, that the model is defined by its resistance in the circuitry. I probably should have grouped mechanics and electric a little bit better than I did, but let's go now mechanically. It's the shaft inertia. But it's, again, generalized, because we're going to get to that in a moment. The mechanical, load itself is defined by inertia, and in this case, damping constant, right? But anyways, for this kind of, again, DC motor, resistance, shaft inertia, inductance, the torque constant, and then the damping coefficient. All right. And we run this model, and we see the results, and we look at angular velocity. If we applied, a voltage of 30 volts, that's the motion you would get. And again, that's again based on these parameters, right? And then what we did, though, is we kind of, again, I think a move towards mechanics is to get rid of, what I like about electric motors is they truly are kind of electrical and mechanical at the same time. Because the ultimate output coming from a motor, in my opinion, actually, it's not velocity, it's torque. Okay, and the torque scales with current, and for that reason, it's kind of important to think of them as kind of mechanical as well as electrical, and that's why things like stall torque and no load speed are such good parameters for defining a motor, right? And a couple of reasons for that, but I'd say with regard to what we're doing in this presentation is that it's really about choosing the right motor for the right application. And stall torque and no load speed in a way they kind of map out the operation, that a motor can handle. the maximum torque you can have is the stall torque, and the maximum speed you can have is the no load speed, and the actual operation of any motor is going to be somewhere in between for each of those. Okay, so so anyways, hopefully that makes sense. And certainly, if you ever have to buy a motor, you want to know what your torque and speed requirements are going to be, and you're going to choose based on stall torque and no load speed. All right, so that's the first thing we did. And so then, but we're still kind of doing this with this, again, kind of false application, which is we're just spinning a constant inertia shaft. All right, and so you know, I'm not going to say that this is a better performing model, but it's one that gives us options as we move forward. Okay, and so the basic idea was to take all this and just bring it outside, and mathematically it's identical to what we did here, and you'll see that what I'm going to call this even electric motor. It's really kind of interfacing with the mechanics through inputs and output ports, and that is a DC motor configuration. So I'll just call that the DC motor, and I'll call this the mechanics with the, oh, I already have something called DC motor, so let's call it something really clever like DC motor 2. Okay, all right. But I really like the interfacing that it sets up, which is motors are responsible for creating torque. That torque gets applied to some sort of mechanism, and that mechanism will move, you know, certainly it'll move in various forms, but it will also move that axis according to what that mechanical load will be. And so only through the processing of that torque through a real mechanical application do we really get a reasonable, you know, relevant angular velocity, and that gets fed back, and of course that's used to identify the back EMF voltage, which is certainly part of the electric circuit calculation, right? And anyways, I guess this is probably why that's words like that, but unless I change something between now and, yeah, all three of them are essentially predicting the same thing. So basically 3 curves right there, red, blue, and yellow. The red, of course, is the last one drawn, and therefore it's on top and we can't see the other two. So to me, I love seeing stuff like that because it means my presumption is correct and that I am accurate and I can move forward. Okay, so again, just to kind of meet folks where they are, I'm going to kind of do this. I'm going to go Control C, and I will open up a new Simulink model. Just paste this in. Okay, and yeah, let's do this one even. Again, we just proved they were identical, but this one gives me better options, so I'll paste this one in instead. So what's the difference? Of course, instead of resistance, inductance, and so forth, we will do this. And it'll be nominal speed, stall torque, and nominal voltage, I'm sorry, stall torque, and no load speed. What I also like about this is it was a very nice kind of check to kind of prove to yourself that you have done the algebra correctly. I will show you the algebra too. Let's go to PowerPoint right here. You know, the idea of stall torque and no load speed is really the definition of the conditions of stall. What do we mean by that? Well, you know, it's the basic idea of I got a motor and somehow I'm able to clamp that shaft so mechanically it cannot move. Well, there's a torque required to prevent that movement if you're really applying a voltage on a functioning, you know, motor. You know, and so whatever it is, you know, the applied torque on that shaft will be the stall torque, right? And so under that condition, you know, there's going to be a current that's going to be flowing through that circuitry, and then we also know that it's going to be constant, and so di dt will be equal to 0. Omega, by definition, is 0, and of course, if omega is 0, d omega dt is 0. And so you take these fundamental equations, you know, that's basically Kirchhoff's law, that the applied voltage will be balanced by the inductive voltage drop, the resistive, and then the back EMF. And that the electromagnetic torque, which is equal to K times I, very cool and convenient and actually quite obvious if you do the analysis, is the same, the torque constant K and the back EMF voltage constant K are the same thing. But anyways, come back to this. Well, T is equal to K times I stall, but the omega dt is equal to 0, and so all that's equal to what we're calling the applied torque T app, which will be equal to the stall torque. And so, anyways, this equation reduces to this simple expression, and this equation reduces to this simple expression. If you do the algebra, you get essentially a calculation of resistance based on stall torque. All right, and for right now, K is still in that calculation, but when you go to no load speed, well, what's that condition really about? Well, it means that you can no longer apply any more current, okay? But actually, even before that, what do we really mean by no load speed? Well, what we really mean is no load at all, that there is zero torque generation. It's really when you get to that kind of definition. That's when you kind of recognize, oh, I is equal to 0, therefore di dt is equal to 0. The speed, omega n, or no load, is, omega is equal to omega nl, the no load speed. And because it can't get any faster, it's not changing, d omega dt is equal to 0. And with that reduction, you basically get this Vn is equal to K over omega nl, and we plug all that in, and we get basically, very nice expressions for both K and R. All right. So, anyways, let's kind of get back to where we were. All right. And these are our values we're choosing. We may change them. It's all contingent. Oh, let's kind of do this thing I wanted to do, which is let's scope torque and no load speed. Right. And again, notice the voltage needs to be 30 for this to work. All right. And so with the initial condition of 0 velocity, well, the yellow, that's the first one going in. Well, that starts off at 30, and we actually are watching the velocity. That's what the blue line is. All right. And so we do see it starts off at 0, and we do see as the velocity progresses, it reaches a bound, and that's our no load speed, which we saw was defined by 30 as well. And we see also that as it hits its no load speed, that torque reflecting current is equal to 0 as well. That torque will be equal to 0. So, anyways, now here's where I wanted to get. Okay, all right. And so this was a guest lecture, and that one of my colleagues is the regular lecturer, one of my friends, and so he asked me to do this one because he had a conflict, a time conflict, a schedule conflict, but he also thought it was a good topic for the class. All right, and so he had already done his share of control. He'd done a little bit of, I'll say, describing how feedback control can be used to control a DC motor. And actually, I think the way I'll do this, again, I'll do a little bit of a shortcut, is I'll kind of open up a model where I'll bring in his controller, right? And it's very kind of explicit and kind of straightforward, and that's why I kind of like this. You can kind of see the model so well with this, right? And so I'm going to copy that, and bring it in on the model that we're working with. All right, and I'll plug that in. Right. Again, PID, it's the basic idea of, well, what the error is, the difference between whatever we're trying to control, whether it's angular velocity or angular position. The difference between what it is and what we're commanding it to be, that's our error. And we are going to apply a voltage that will have a component that's going to be proportional to that. This is what we call essentially our proportional gain. A component that's going to be integrated and then again multiplied by a gain. So that'd be our integral gain, and then a component where the derivative is taken, and we'll multiply that by gain. That's our derivative gain. Right. I think I'll kind of start off 0 there, and maybe we'll make this 1. Okay, and I'm kind of just going to see what happens at this point, because in a way I haven't practiced this one a whole lot, but I want to essentially create the feedback loop. Again, as I mentioned, that the error will be the difference between what we're commanding it to be, and we're going to command it to be 30. Right? And we're going to compare it. Okay, and I think I'll do position control. And so I'm going to construct my position by simply integrating the angular velocity. All right. And I'm going to feed that back. Now this is really important what it says there. W, that's a common symbol for angular velocity because it sort of looks like an omega, and that's what we really would like to call it. But anyways, W, and then I got in parentheses units, radians per second. Well, what's 30 here? Do I really want to do 30 radians? I'm not even sure how much that is. I think it's a little bit short of, that's 2 pi, right, each revolution. So it's a little bit short of 5 revolutions. But anyways, let's go for 30 degrees. And if I'm doing 30 degrees, .80 divided by pi. Of all the gains I've ever assigned values to, probably 80% of them are either 180 over pi or pi over 180. Yeah, I'm doing that one all the time. But basically I just, oops, and I got it wrong. I need it to be the other one. So basically I want to convert from degrees, 30 degrees, to radians, whatever that will be. Okay. And I think I will do the other one, though. I'll just kind of put it on the downside here. Okay, and we'll put in 180 divided by pi. And put a scope in. And I have no idea, actually, how well this will work, and so it's just going to hit run. And that apparently is position, and you know what? It's not so bad. And that's all proportional gain. Right? You see that right there. Right? And we might play the game of trying to make that happen a little faster. And so we add a little more proportional gain, and maybe we'll try 5. I won't go too much further on this. All right, and we just get it faster and faster and faster. Okay, and so in a way, there's always this oscillation, and I think if you're kind of observant, maybe in tune to the idea of waves and oscillations and frequency, you might recognize the frequency is very much dependent on the proportional gain. And there's a strategy to kind of deal with the overshoot that leads to, which is to apply some damping. And again, I'm going to just apply a little bit right there. Right. And see if I can kind of reduce that overshoot. And whatever I did, I just made it way stiffer. And so I'm not patient enough to kind of wait for that to work its way out. So I'll just kind of come in here and I'll reduce things a little bit. Right. And I'd say somewhere between 0.1 and 1, maybe I'll do one more attempt at this. I'd say we reduced it a little bit. But again, I don't want to, claim to be good at doing that. And I do want to acknowledge that there are people I know, and there's a number of people at MathWorks who are really good at that game, and they know how to analyze according to the frequency domain, and they will use Bode plots and root locus plots and really kind of play this game of response versus stability, and be very good at this in a way that I can't be, right? But fortunately for me, there are alternatives, right? And so in a way, that's what this lecture will be about, right? And so I think that's about as far as perhaps I personally should go, but certainly, again, colleagues of mine could open up the control system toolbox, and perhaps even the DC motor is such kind of a piece of cake for them that they could show you all kinds of cool ways to do this. But what I like about this, okay, and so what I'm doing now is going into the Simulink library and grabbing the block that does PID. Okay, now this is a very optimizable, it's also very reconfigurable, and so I'm going to show it to you. I'm going to go look under the mask, and you're going to see all kinds of stuff that's going on. That essentially, most of the time is mathematically doing what I showed before. All right. So, anyways, but what I'm going to do now, though, is I'm going to click on this button. This is the tune button. All right, and there's something. Well, it may appear mysterious, but I'll say it's beautifully informed on the approach of controls. And so what we're doing is, you'll see that when I click on this tune button, that's going to linearize the plant model. It's going to do things like, identify the open loop Bodes and open loop transfer functions and all this kind of stuff. And based on that, it's going to take these methodologies that, again, a number of my friends are real masters of, and it's going to figure out optimal gains for this. All right, so there's KP, there's KI, there's KD, there's N. Why did it need to kind of sample the model? Well, because KP, KI, KD, and N absolutely care that it's a DC motor with the parameters that we chose it to be, with the mechanical load that it's really applying this to. All right, and so again, I like this quite a bit, and the thing I'm going to do now is just kind of show that you haven't given up control of this at all. And I'll say that again, as you consider both faster and more robust, you're playing that game between response and stability. And in general, I just like to hit the faster button, right? And so with that, I'd say a little bit stronger gains, but I have much better response, which is measured by things like rise time, settling time. And you'll see that as it, again, optimizes the response, that there is an overshoot, all right? And in general, you want to minimize that overshoot, right? And I won't go much further than that. I'll go ahead and close that. I'll update the block with the values that it identified for us. And I'll close that, and you'll see all those numbers are in there right now, right? And that's too bad it kind of cleared what was there before, but I'll certainly show that we got a pretty nice response now. And so we commanded 30 degrees, and we're hitting 30 quite well. All right, and so we got a little bit of an overshoot. And this is where I'm going to kind of put this on the shelf for a second, all right? But we're going to kind of come back to this, all right? And we're going to get a little bit into this thing that there are two issues here why we're getting overshoot. I'd say the first one is that we're asking it, starting off at a 0 angle, we're telling it, well, I want you at 30 at 0 seconds also. We're essentially applying a step change on angle, meaning that we want it to very discreetly go from 0 to 30 in 0 seconds, right? And one of the beautiful things about PID algorithms is, well, they kind of acknowledge, well, I can't do that. It's a violation of F equals MA, which exists kind of in a rotational form, at least in this kind of two-dimensional problem, is torque is equal to inertia times alpha, the angular acceleration, right? And so that's a very reasonable response. It only overshot about 4 degrees, and got to 30, clearly in less than 1 second, right? So that's kind of cool. right? And so you know, there's the idea of the impossible request, which is that right there. But there's also kind of this idea of carrying through lots of state, you know, variables, DI, I, omega, and position to kind of get what you need is far more complicated than what really can be handled. And so PIDs are nice. They're empirical. They you know, they will work, and there are methods that can tune them to really get, you know, very favorable performance and responses for your system. But if you really need to be accurate and you cannot tolerate overshoot and stuff like that, there are ways to be better. Okay, and that's what this lecture will kind of move into. All right, and so I think the first thing I'll do, okay, what we got right here? We got 30, 30, 30, 1, 1e minus 5, and 0 damping. Okay, fair enough. All right, so let's go back to my DC motors. Right there, right? And we already proved ourselves that these are all the same. So should be getting the same response with this. So let's see, how do I select all this? I think that will do it. Let's go Control C. Let's paste this in like this. Okay. And let's make some room. Make that a little bit longer. And let's replace this. Okay. All right, and so let's go to the scope. Let's hit run. So that was bad presentation on my part because we had already kind of zoomed in on the range on this. And so this is the exact same result. You can see that's about 4 degrees overshoot. And if you kind of compress the scale to about 2 seconds, I think it looks pretty close. So that, please excuse me for that. All right, I'll give you a little bit anal at this point and just get those lines a little straighter. All right, and okay, and well, here's an idea. Kind of bring this up. This is how this lecture actually started yesterday. I did this live, and what I did, here, I'm trying to get to my YouTube account. It can be a little embarrassing showing your YouTube stuff, but let's go to playlists, and that this whole session really began right here, and it's so it's my YouTube channel, Terry Dennery's Engineers Studio. And I went to DC, control with the DC motor control with an Arduino hardware. I'll even show it to you. I got it right here on my desk. But I don't want to spend the whatever, probably 10 to 15 minutes it would take me to do this live. But if so, anyways, here's the Arduino. It's on a Arduino motor carrier. My motor is this kind of $20 DC motor with an encoder that I bought off of Amazon, and you know, basically kind of started off showing that I can make that thing turn four revolutions in 3/4 of a second and do it with almost zero overshoot. All right, and that the ability to avoid the overshoot, or at least to minimize it, that's explained actually very well in this first little video right there. And I'll just point it out that it worked because I created what we call a feed-forward method, and feed-forward methods are basically where you put your understanding, your information, your knowledge of what the system is. And in the case of a DC motor, mostly it's torque constant, it's no load speed, it's inductance, and damping, and shaft inertia, if you're able to identify those things. And so there are other videos where I kind of show how we identify them. But the point was made very clear at the beginning of this presentation, that this idea of using what you know, pour it into a feed-forward algorithm, that this stuff really works well, and in a way, I think it's pretty clear to say that that's the way it's done, right? And so I meet with professional customers all the time, and of MathWorks tools, and they're always looking for advantages to get more accuracy, more response, and more kind of robustness and stability for their calculation. Okay, so and it turns out this kind of feed-forward approach kind of goes hand in hand. Actually, I think that this is a good point to kind of deal with this, which is the simplicity of this problem is a bit of a problem, right? And so we're going to switch now. Let's get to it. I created these models right here. I think I'll even kind of package these. All right, so let's go like that. Create subsystem. This is what I call forward dynamics. It means I'm sending motor torque in expressed in Newton meters, and I'm going to get the response of the motor. So we're going to create that. You'll see motor torque and motor underscore M. Let's see, how do I want to do this? I want to kind of keep it simple, or at least let's call it focused. All right, and I think I should show you what this is. So let's go ahead and simulate it. Let's hit the run button. And let's bring up the animation of that. Right. Stop, reset. Okay, and we got 2 beams there, and here's one we're just running. Again, I'm trying right now. I know I'm showing a lot, and I want to make sure that this is not confusing. All right, so I think the best way to do this is let's hide this one right now and essentially remove it from the calculation. So it's merely commented out now. And this one, I want to give it a little bit better name, so when we kind of focus on it, you'll see what it is. And so I'll call it Terry horizontal bar. The space in between Terry and horizontal. Okay, now let's run it again, and okay, this time we'll just see it by itself. All right, and there it is, Terry horizontal bar. Okay, all right, so hopefully that's being, well, let's do this even too. So let's reduce, move it up slightly, and observe it one more time. So basically it's a simple pendulum, all right? Okay, but in truth it's actually a motor, and it means that we can send a torque in, and we can, through that torque, kind of control its movement, right? And that's the way to put torque in, is right there. Right? And I guess, again, it's always good to do a little bit more demonstrating to kind of prove your point. And I think I can show the effect of the torque here. So I'll hit the green button right up here. So I'm running it from the animation window. Oh yeah, clearly 1 Newton meter is going to push it up, and once it's going up, there's no stopping it. It's going to just continue to gain speed. You'll see a little bit of what they call that strobing. Yeah, so the animation gets a little bit weird. Right? Anyways, I think that's enough. I'm not going to belabor this too much. All right, so I'm going to go Control C. All right. some of these things down. I don't think I'm going to need the DC motor anymore, and if I do, we'll just kind of bring it back up. So let's go ahead and say no on that, and let's get to the model we were working on. Got way too much open right now. Right, so where is it? It is right there. It's untitled. We still haven't saved it, so all this is fresh. Right, and again, I'll just run it one more time before we start changing things, and this is kind of where we stand right now. Right, and I think we're reasonably confident we're accurate at this point. Right, so what I want to do though now is I want to paste in Terry's horizontal bar. All right, and now I need to kind of fix something. And I don't know if it's really broken, but I do need to kind of address something. Okay, first of all, why is that line thicker, right, than that line, right? And so let's go to bus selector. Okay, keep on missing. Yeah, you should do it this way, go back up, yeah. Okay, so this is a bus selector, all right? And you need to kind of connect to a line before you really should open up the block parameters on a bus selector, because what's going to be filled in is really the contents associated with that line, all right? And so it's essentially a stream of information. And I think that the word bus, I think that actually came out of the electronics industry, and it's a way to essentially pack up a bunch of sensor signals, perhaps in multiple wires, whatever, but also kind of put an interface on it so that you can kind of go pick out what you want. And so anyways, we're going to pick out motion. Okay, with regard to this, this presentation, we haven't explained quite well yet, what we mean by motion, but I'll just kind of reveal it right now. And I think I'll do it this way, DEMUX, DMUX. Right. And that this is kind of a packing of signals too, but these are going to essentially think of this as an array with 1, 2, and 3 elements, right? And that the definition of what we call motion is really the combination of position, velocity, and acceleration, right? And why is it 3? Well, it's because F is equal to ma is in a way the reason, and that mechanically it's generally 2 states are really carried to define, the current, I'll say, condition of that mechanical system. And if you think of, kind of what we're doing with this example, a horizontal pendulum, think of it as its angle and its angular velocity, so theta and theta dot, right? Are its 2 states, and then the driver of it, of course, will be the second order derivative, which will be theta double dot. So anyways, but what I want to also do is let's delete that. Let's rename this. Let's call it angle. And again, I always like to put in units, radians per second. And that's pretty good. I'll put that right there. Let's get Terminator, just so we don't get any warning messages. Let's kind of plug those off like that. All right. And now I think that this is getting really kind of clear that we're defining an interface between electric motors and mechanics, right? And so that I'll even make the boxes the same size. Oops. So click on that, control, nope. Click on that, shift, click on that. And I'll go to format, and I will match the sizes. Okay, all right, and so mechanical loads change like that. Where did this block come from? Well, this came from whoever designs or models the mechanics, right? And so, perhaps we're seeing a little bit of kind of this idea of groups working together in collaboration. But anyways, and if they are going to work together, they better be on the same page with stuff like this, which is not only that it's an input on torque, but it's an input of torque expressed in Newton meters, and it's an output on angle. And look at that, I got an error there. We did kind of mess up. I'll back up a little bit just to kind of show the error. And this is radians per second. The fact that this guy's capable of measuring angle, maybe I want to standardize a little bit more on angular velocity, but I kind of doubt it. And so I'm going to just, again, kind of make the call and say, in this case, our angle will be, our output, our measurement will be angle, not angular velocity. And so I'm going to delete that, pop that in, and of course, we don't need to integrate that anymore to get position. All right. Okay. Now this worked so well last time. Well, I don't think it's going to work nearly as well. Wow, that worked pretty well. Okay. And got kind of a crazy oscillation at the beginning, and you might even argue that my mechanics is outsized by how big this motor is, right? And again, nominal voltage is 30, stall torque's 30, no load speed's 30, inductance 1e to the minus 5. And we'll kind of work on this one though too. Oh, here's always a good thing to check, right? Is we got voltage right there. And you'll see there we're basically requesting, what is that, about 900 volts? Yes, with a big oscillation, right? So along the lines of what I really wanted to get at, which is this is not the way you do it. You do not use a single PID to essentially control, I believe it's 4 operational states for this overall system. And so I'd say that kind of the reality of this will kind of come through. Actually, and this is not, I'd say, the way to do it, although it's a useful thing to do, right? That it probably is the way it is done sometimes, but I'll put kind of the limits on voltage into the controller so it can never ask for more than an absolute value of 30 volts, and let's see how well it does that. And again, I would say that is not awful. I am not, I'll say it this way. I'm kind of impressed it did that as well as it did. All right, and if you look at that in an animation, you get, do that one more time. Stop. It's kind of a weird motion, but absolutely it could work. And so, so I'm not going to condemn it, but I'm going to just say that I think there's a better way to do it. All right, and where we're going to go really is that transition. Okay, again, we've already talked about the impossible request, which we're saying go to 30 degrees according to whatever your PID and your DC motor will allow you to get away with. All right. Now, the other thing we're kind of dealing with here is, well, we're using a motor that perhaps is capable of way more torque than we need, and that we're, perhaps limited by what range of speed it's able to operate under too. But again, these are good things to understand, stall torque and no load speed. All right, so the way I think this is best done, and so I'm going to just kind of start from scratch again. Is to do what they call inner loops and outer loops. All right, and so the way you do that, well, you kind of begin with the outer loop. All right, now I think as we go through this, why they're called that makes more and more sense too. But let's go here. Let's go PID. Oops. That's my own kind of configuration. You see it shows up in Terry's electrical mechanical components. Right? So this is one that ships with Simulink. Right? So we're going to use a PID again, right? And we're going to adjust directly the motor torque. We're not going to worry about the motor itself and what voltages and currents need to be. We're going to just say, if I have this ideal kind of torque delivery system, I want its torque to be adjustable to get the movement that I'm going to command. Right? And so let's go ahead and construct that error. I'll get a sum block. And I will feed back that angle in radians. I will assert 30 degrees again. Right. And let's measure it with one of these two. And let's put a scope in there to get it. Okay, so that's basically what you'd call an unstable controller, right? And as I mentioned earlier, that's what control engineers worry about. They're absolutely concerned about stability, at the same time doing accurate control with rapid response, right? But it turns out KP and KI, probably both being one, is probably way more than you need out of this, right? And so again, it's the idea that this PID adapts according to the problem at hand, right? And or always I'll say it this way, the values of KP, KI, KD, and again that fourth parameter N, which kind of defines the quality of derivative that you might calculate, you know, that those parameters can adjust to apply to all kinds of applications. You know, and again, it's a remarkable thing, right? And so we do this whole method and we linearize the system and everything, you know, kind of here's where the values it will give us. And I'd say I'm not happy with rise time of over a second, nor kind of a settling time of almost 14 seconds. So I will make it faster on my own. And perhaps I like that. It's kind of interesting, all three are negative, right? That makes me think I made an error, right? And in a way, the method is kind of clear in saying, oh, I don't care, right? And there's your error right there, you know, that's not an error calculation right there. That's, you know, that's adding my command with my feedback. So it's error only when you subtract off feedback. So let's go ahead and do that. But again, it's remarkable that the PIDs will adapt to that, especially with this tuning methodology. So let's go ahead and close that. I didn't update them. Okay, good. So again, we're starting off with KP equal 1, KI equal 1, zero derivative, but this, again, filter parameter in, you know, it'll have a value of 100, right? And so let's go to the parameters. I think we'll see they're all positive this time, which they are. And if we want it to be a little bit faster, you know, those are the values we get now. And I think I'm probably good with that, so let's go ahead and close that. Let's update the PID. All right, and close that. Make sure I get those numbers in. Yes, I did. And so that is really, really interesting. Okay, so what happened there? All right, well, one way you might fix it is, okay, I think I somehow fell short of the faster response I want. So let's go ahead and retune it one more time. All right, but there's a number of reasons we got that interesting response we just got. Okay, so yeah, so I did update it with those values right there. And let's try it maybe one more time a little bit faster. All right, and we'll close, update, and we now can close this. Those bigger numbers are in there now. All right, and now we get to work. Okay, now I think that was an interesting error that we just observed because it revealed quite heavily that, you know, that this linear control approach can be a problem because it is a linear control approach. You know, and what we ultimately are doing with PIDs is we're really attaching really kind of cool, you might call them springs, you might call them rubber bands even, between how we want that pendulum to move and how it's really going to move, right? You know, and if you especially look at like the proportional piece of it, the proportional component of a PID, it's exactly the formulation of a ideal spring. You know, follows Hooke's law to a T. You know, so anyways, that's kind of what PIDs are, and it's amazing that the methods are there to really rapidly adapt them like we just did here. And in general, if I make a PID strong enough, I can get something like this to sort of work. Now again, you'll recall we're going to have to have an electric motor do this, right? And so now I want to address a couple of things, all right? Okay, I want to now address the impossible request. And at the same time, I want you to be in charge of the transition, not the PID, okay? PID's job is really just kind of keep it moving the way we want it to move, all right? And certainly we know we cannot ask it to move impossibly as we do with the step function. All right, so let's go ahead and now kind of get into what I call PBA, or motion. And we saw motion a little bit. Where was that? We saw it, well, we saw it in here. You know, we saw we muxed or demuxed it, and then we terminated out the velocity and the acceleration. All right. And why is this so important? Well, if you do the equations, actually this is what I spent a little bit of time on this afternoon, on the mechanics of a pendulum, you know, that, you know, it's all about theta, you know, and it turns out theta dot, in the case of a pendulum, is actually not that important. But what we get is a relationship between the torque applied, the inertia, and the second order derivative of theta, you know, which is essentially the angular acceleration. And it's an equation that sort of looks like this. It means that if we apply this torque Z, and we have a torque that's going to be produced by gravity acting through the center of mass of that beam, you know, we know that that center of mass is the midpoint of the beam, and therefore it's L over 2, and that moment arm, therefore, is L over 2 times cosine theta. You know, we kind of know what these equations sort of look like, and certainly we're seeing very clearly in this example, you know, that, you know, it's got a dependency not only on position, you know, and that's more the kind of like less obvious one. We obviously know it's got a dependence, the torque, on the angular acceleration. You know, and it's clearly a nonlinear problem because we got this nonlinear function, you know, of theta is involved in essentially setting what the angular acceleration will be. All right, and so anyways, I don't think the linear method. Well, I'll say this: I think it's pretty darn impressive it works as well as it does. All right, and so let's begin by again choosing a motion. We're going to go to Simulink, my browser, my motion signals. We get one of these guys, smooth step. All right. Again, I've got way too much stuff open. Okay. All right. So it's, again, I'll demux it. There's something called a selector, which is a little cleaner, but, you know, I think for our purposes, kind of nice how explicit this is. Right? And so I'm going to go like this. I'm going to get a scope on this. Let's make that as tall as this one is. And under format, we will match the height. Okay. And so then we'll bring the signal right up to the scope, and it will create another port for us, and therefore we got all three of them. Right, and so let's hit run. Okay, and this is kind of showing, essentially position is yellow, blue is velocity, and orange is acceleration. And essentially those are kind of why did I create my own blocks, because I wanted to have perfect calculations of position, velocity, and acceleration. Right? And so as you kind of separate these things, you'll see position on the top, velocity on the second, and acceleration right there. I think it's pretty clear that that's the first derivative of that one. At least it's very credible and believable, and that this will be the first derivative of that, hence the second derivative of the position. So P, D, and A. All right. And so 30, so let's set this up. Let's start the transition at 1.5 seconds. Perhaps go for like 2 seconds, and of course let's go to 30. Right, and so now I'm going to replace, and I need this to be in radians once it gets to the motor, so here's where we'll kind of make our replacement. Okay, and I'll pop that in like that. Okay, and I will hit run, and so 1.5 seconds we should see the transition. All right, and we see it actually works really quite well. All right. Anything I want to say with regard to that? Not exactly sure what that is. I'm not going to fret about it right now. I'll say this. Again, it's not a whole lot of drooping, but it's a little bit of drooping, and I'll just say that, well, let's do the quick analysis on it. All right. So here's what we've commanded to happen. And so the first 1.5 seconds, we just wanted to hold a position of 0. Right. Okay. All right. And so what happened here on the droop? Well, it got to 0 pretty quickly. I'd say that probably by at least 2/3 of a second, it's pretty close to 0. And what happened here? Well, we got our maximum torque on it, at least from gravity, at the beginning, because it's perfectly horizontal. Therefore, that moment arm's as big as it possibly can be. And at the beginning, this is what PIDs do. There's no buildup of the integral term, which is actually the biggest component of the PID, and therefore this error had to be formed for us to have any response from this, and the 11.7 times that angle error expressed in radians, so it's probably a number on the order of 1 it built up to, was not nearly enough to support the torque load that was being applied at that pin connection, right? And after a little bit of time, that error got integrated and built up enough so that once multiplied by this number, it was again able to zero it out. Okay, so that's PIDs. That's actually a good example to explain what integral gain is, integral control is all about, right? And otherwise, in a way, this is better than I hoped for, right? I mean, look at that. That's quite beautiful, right? Let's go here. I mean, almost 0 overshoot. There's a little bit. You can see it right there. Where's that? And this is degrees, so we're talking about a couple of hundredths of a degree of overshoot. Right. Now, see how far we can get along with that. And let's make this maybe 0.5 for the transition this time. Okay, and we're going definitely much more, and we're about 1/2 a degree at that point. Again, you might be perfectly happy with that. right? You might not like this, but there are lots of ways to deal with that one, and let's not really even be concerned about too much yet. But I'll just say that the errors we're seeing and the overshoots we're seeing, and certainly when we asked the impossible requests, well, how do we approach the impossible requests? Well, let's do it this way. Let's make a transition in 0.05 seconds. Okay. Now, it seems awfully fast, but that's real. And we begin to see something that looks quite a bit like what the step response was. All right. And so anyways, let's now fix this, right? And so now I'm really going after the linear control approach, right? And so I think the easiest way to do this, actually, here I'll show this model. This was the other thing I was working on today. It's a little bit of a mess, so hopefully this is not too much of a problem. Okay. Boy, this is a mess. Okay, let me get into this a little bit. All right. So we saw that equation in my PowerPoint slide. Okay, and it's essentially expressed in this MATLAB function right here. And so theta second derivative is calculated in terms of the applied torque and the current angle, as well as the mass, the gravitational acceleration, the length, and of course cosine theta. All right, so we saw that equation a little bit earlier. All right, and we simply integrate that. All right, and this part of this is merely, I'll say, something that I validated with our mechanical model. Now, we haven't talked so much about this, but let's go and get into it a little bit. This is Simscape multi-body. Notice lines don't necessarily have to have arrows anymore, and that's because we're talking about mechanical structure at this point. And the structure of this mechanism ultimately is that there's a rotational joint connected to the ground on one side and connected to the bar on the other, and that we can apply torque through it, and that we can measure all kinds of great stuff, including the torque we put through it, but as well the angle, which is called Q, the angular velocity, which is called W, and then the angular acceleration called B. And you'll see from this we can construct things like power calculations, which would be torque times speed, and this is essentially the creation of a very useful output which we pump into a bus, right? So this is Simscape multi-body, and of course the bar itself is perhaps the most important part. And there's that bar, and based on that shape, and we parameterize with a MATLAB variable its length, so we can make it longer if we want. But that geometrical definition of length, width, height, defining a volume multiplied by density, that then leads to the mass properties. And so you update this and you see mass, but you also see moments of inertia and center of mass and important mechanical parameterization, right? And position, of course, is everything. Again, part of Simscape multi-body is, how do you position these, and you use all kinds of rotational methods like quaternions, rotation matrices I like, and Euler angles and stuff like that. And then positional offsets are kind of easy. X, Y, and Z kind of Cartesian is typically the way you do it. So that's the kind of quick and easy, and you don't have to be an expert in rigid body mechanics to do it kind of stuff. Where kind of the approach I took here, I wouldn't call myself an expert, but maybe I can do a little bit. And so I did basically the pendulum problem. So with Simscape multi-body, we got a more kind of generalized methodology, but I'd still say if you do know the equations in motion, they can be pretty useful too. All right. And okay, so why is this important? Okay, well, it's because if we can do this, which is send in torque and angle and get out of it angular acceleration, well, it means we can do this too, which is send in angle and angular acceleration and get torque out, right? And so this is essentially what I'd call the inverse dynamics, meaning tell it how it should move, sending in angle and angular acceleration, and tell me what the torque is, right? Okay, and so this is what we're going to do now, right? Is that we're going to use this. You can kind of see this whole model was about setting up something which we're about to move into. And yes, PIDs are still useful, but you'll see that they get, I wouldn't call it relegated, they get focused to what they're really, really good at, which is making error go away. All right. And so I think the way I'll do this now is I will disconnect that. I will paste this in. Motion PVA. This time actually expressed in degrees, right? You'll see the converters part of this block. Not sure I like that right now, but it's a good thing I caught it because it means I go directly from here into there, right? And so again, we're going to 30 degrees in 0.05 seconds. Again, let's start off with the easier problem, and let's do it this way. Now, isn't that interesting? Looks like it's doing really well, and then all of a sudden went crazy on me, right? And again, it's an unstable controller. It goes to like 10 to the fourth, right? So what's so great about this inverse dynamics approach? Well, my claim really was not replace all your control approaches that were with feedback with feedforward. That actually is a dumb idea. Okay, but what I'm really claiming is what you know about this system is really, really useful, right? And so the ideal really approach to this, I think I got it. I'm gonna do it this way now. It's the combination of the two, all right? And so the way we're gonna do this now is let's use one of these add blocks. Pop it in here. Let's get that feedback right there. Let's move this up like that. And let's put this feed forward in like that. Okay. And I think we got it. Let's click on this. Let's hit run. And rescale. Boom, we're perfect. Okay. So that's, other than the droop at the beginning though, we were doing almost that good with pure feedback. And we really needed to speed this thing up before we could really really kind of reveal the error. And again, that's why PIDs are awesome and people have been using them forever, because they really did work so well, right? But we saw before, when we sped it up, that it couldn't deal, right? So let's hit run, and now it can deal, okay? And and with regard to the endorsement of this kind of approach, well, we're kind of working on the simple problem, and perhaps we'll kind of finish this whole thing up, which I did in the lecture yesterday, with a little bit more challenging problem, right? Okay, but before we do that, I kind of want to return to our DC motor, right? And my claim, is that if I had a ideal torque generator and I could control it, that's basically the problem we just solved, right? And so now my claim, and there's kind of a way we know we can do this, right? And perhaps I'll do just a little bit more setup before we bring in that DC motor, is if that's my torque, this will get a little, well, I shouldn't say messy, but I'll say I do want this to kind of be in radians, so I'm going to go on this side and get that. Oops, I don't actually want radians, I want radians per second. And so I'll do it this way. Okay. And now I want, where it's now being expressed in degrees per second, let's get that in radians per second. All right, and let's run this one last time. And we'll just kind of scope this like that. Okay, and let's hit that. Okay, and let's see what's on top. Top is torque, and on the bottom, the blue is velocity. And so we're going to see a speed that looks like, I'd say, well, let's just say 20, and it's a little bit shy of 20 radians per second. And the top torque looks like it's about 7, so let's say it's around 10. Okay, and what we're doing with this really is just, you know, what you always have to do when you use real motors, which is you need to size or choose the appropriate motor. So now let's go get our DC motor. Oh, I shut it down. So let's go in here, DC motor. Yeah, there it is. Control C. Kind of delete all that stuff. And let's paste this in. Okay. All right. And now we're going to, again, kind of get into kind of the feedback loop that we're going to use here. Right. And so it's going to be PID. Like that. All right. Let's get a sum. That. Move that. Okay, and let's not make that error where I left it as plus plus. Let's make it plus minus. And so do PIDs. Do you have to do it only on angle? Of course not. It can be whatever you want it to be. And so in this case, we're going to do it on torque. And the term that often is used here is called a current loop. And that's because torque and current are going to be proportional. You know, and it's K times I is the torque constant times the current. That's going to be the torque. Okay, so this truly is conventional, even if the term torque control sounds a little bit strange. But it's the idea that we can command torque, compare it with what is measured through current, and then that error will be operated on by the PID as well. All right, and so that looks pretty good. Of course, we know that angular velocity needs to be filled by the mechanics, and here's where I'll go back into this model, and I will kind of remove the terminator on that, and I'll just call it W, and I'll make it radians per second. Okay, so that's available for us now, and I think we need a little bit more space. So give us the room we need. Yeah, kind of. Okay, so we'll delete that. Bring that in like that. Connect, and there's your torque delivered by your DC motor. Right, and I think to kind of complete this, let's come out, take that angular velocity. I think I got all the units correct, and let's see how we do. Oh, do we have the right motor? What did we come up with again? I shouldn't have deleted all those scopes. I think it was like 20 on stall torque, and I think the rotation was maybe like 10 radians per second. Well, we're about to find out. And again, we haven't tuned our PID, and let's do the easier problem first. And so let's bring the commanded motion back down to like 2 seconds. It's kind of what you get, all right? And we're kind of getting the general notion of what we want, and we certainly see it wax in at 30 ultimately. And I think I will try tuning my, again, I introduced that term earlier, but there's my inner loop. The fact that we essentially have a loop because of mechanics, maybe I'll bring that up here, and maybe it's a little clearer that that's, well, some people would argue, well, that's controls too, but I don't want to get into that philosophical argument. But what we have is two active PID loops, and this PID, functions based on this feedback of torque, right? And this PID operates according to this feedback on angle, right? And that this is the new one that's untuned, and so let's just kind of tune it to. Showing parameters. So a little bit different, and maybe make it slightly faster. Is that okay? Yeah, I think it's, yeah, that looks okay. Basically, it's almost all I. I'm sure there's a good reason for that, but I'm not going to dive into that one for right now. And so let's go ahead and go with that. I is kind of nice though, because I is numerically pretty stable. So, and there you go. And so that's with the DC motor. We're doing quite well with that. And now we know how much voltage it takes. For that matter, we could go ahead and figure out current too, but again, that's being expressed by the torque, and in a way we kind of already knew what that was. Right? And so for a 2-second transition, doesn't need much voltage at all. It goes up to, what is that? Maybe like 3 volts. Yeah. And let's try the harder problem, see if it can handle that. And that's that the transition occurs in 0.05 seconds. So that's a little bit interesting. And I want to give that one a little bit thought. Am I okay with that? And perhaps I might go in and do a little feed forward on the voltage piece of it too, which can be done. I think, again, if you get into the DC motor, that you could send in torque, and I think it's something like, well, torque divided by K, that's going to give you your I. And then if you know I, you know how much I times R is, and if you perhaps want to even take the derivative of that I, you multiply it by L, L di dt. And then finally, we know, based on our commanded motion, what the angular velocity be, and that'd be omega times K. So probably some games like that could be played, but I'd say for the most part I'm pretty happy with this. And again, I want to kind of acknowledge PIDs are really popular. They have an incredible history of success because they really are a really, really great idea, and that they work incredibly well. So here's kind of the last demo to just kind of wrap this up. And it looks like we'll probably come in about an hour and a half on this overall presentation. And so this last demo, well, I'll just allow my desktop to be messy. It'll get confusing, but let's see if I can pull it off. All right, and let me go into this one. It's called PMSM Mechanics. What I'm really tapping into, and I encourage you, again, check this out on Terry Dennery's Engineering Studio. AC motor. View the playlist. In this first demo right here, look at that. It's less than 5 minutes even. Let's see if I can do it in less than 5 minutes then. All right. And but this series kind of gets into three-phase AC motors, which are incredibly important. This idea of permanent magnets, synchronous motors, and this idea of field-oriented control. It's brilliant, it's clever, it's incredibly useful, and hopefully it'll be useful for you. So let's go back to Simulink. We'll go back to MATLAB really. And yeah, let's just kind of clear workspace, clear commands, and open this one called Velocity Control My Way. Okay, I'm probably being a little bit of a smart aleck calling it that way, because what it really reveals is I don't believe in velocity control. What I believe in is always torque control, and I think that's truly what a motor delivers. It's torque, it's not velocity. And we convince ourselves they're velocity. Again, I'm a little bit on a what's that word? I'll just say I'm voicing opinion here, but we know that terminal velocities have a relationship with voltage, and that's essentially what the no-load speed is. But there's always some transition to get there, and that transition occurs because the motor is capable of delivering the torque that can deliver it. So, anyways, but this thing starts out. I'd say it starts out as simple as it possibly can be mechanically. It is a rotation of a constant inertia shaft. We've commanded the motion that we're seeing in the top figure, the top graph. And again, blue is on top of yellow, and therefore now I'm doing nearly perfect, right? But it's a constant inertia shaft with zero damping, right? And so, and it was quite easy to be predictive of this one, which is, this is that block I was telling you about, the selector block. Takes off the third component, the acceleration, multiplies it by inertia, and gives you that torque. And that torque then is fed into what I'm calling an electric drive, and the calculation of what your voltages on terminals need to be, takes place to deliver on that torque, right? And so, what I'd say with regard to AC motors, I think this guy, there's a guy at MathWorks named Graham Dudgeon, and Graham Dudgeon is awesome at this stuff, and he kind of taught a lot of us, how all this stuff works, with AC motors. And it's probably about 4 or 5 years ago. I really was, I'll say, very, what's the word? Serious, diligent, whatever those words kind of connotate, to really understand AC motors a lot better. And so Graham graciously gave me probably like at least 2 or 3 one-hour sessions, and we just kind of really hashed it out. And so he explained a lot of things for me quite well, and then I just kind of dived into it too. But anyways, when I got the AC motor to deliver the A, the B, and the C voltages, essentially there are 3 terminals, that looked like this, I knew I kind of had something that was working properly. And so at this point, you can see it right there, we're spinning at a constant speed. And if you do your math properly, you'll kind of see that these 3 voltage waveforms are 120 degrees out of phase with each other, right? And that's just a good characteristic for AC motors. And we also see, again, with my simple mechanics model, well, once I get up to speed, all of this is being done to essentially accelerate the inertia. That the current consumption is only going to take place when we are accelerating. And so that's again a nice validation. Again, we see something that sort of looks like that idea of, I'd say, waveforms that are, let's call it 120 degrees out of phase. All right. Okay, so kind of a cool thing. And I'll just kind of, again, get into, well, how am I able to do this? Because I'm a mechanical engineer, not electrical engineer. Well, that's because Simulink has something called SimScape, and SimScape's got loads of, really important, components, and one of them is the permanent magnet synchronous motor. And so we essentially have power electronics right there. We have a field-oriented controller, which is dictating the voltage that we'll put on the 3 circuits. Essentially, that's A, B, and C. Okay, the motor is defined in terms of things like, well, resistance, inductance, flex linkage, which is kind of associated with torque constant, and then there's this thing called pole pairs too. Again, I won't get deep into this, but I'll kind of get into field-oriented control. A lot of, I'd say, trigonometry, at least a lot of sines and cosines are being kind of employed here, and I did it here just because I thought MATLAB functions were kind of cool. But we certainly have tools in like the motor control block set that are really, really good at kind of figuring out these waveforms. And this thing called the Clark transform, I won't get into the depth on it. I will say that the basic idea is if you got a, well, there is one image. Do I have it? I don't have it open. I'll just kind of rely a little bit on some who are watching this will know about the Clark and the Park transforms, and that those are being used in this field-oriented control approach. The whole idea that torque is kind of commanding everything. We see a little bit of that there. And there's a little bit more to the controller. Where did I put that? Yeah, let's not worry about it. Okay, yeah. But let's, now I'm kind of curious how did it say, oh, ABC torque. That's all the FOC. Okay. Okay, anyways, but what I want to kind of do now is open up another model, right? And again, this is taken straight out of that video that I was pointing out that I did in less than 5 minutes, right? I think I'm failing miserably to break 5 minutes on this one, but let's go ahead and do this. And what I think is kind of cool about this is I'm going to kind of show you, this is what the workflow will look like as you kind of master these tools and, you know, really kind of absorb kind of what we spent the first hour of this presentation on. All right, is that you have a mechanical model, essentially the outer loop. All right, we command a motion. The motion we just commanded is rotate 90 degrees. Right, and you see it does it really well. Right, and here's the torque and speed required to do that. All right. Okay, so now let's get that AC motor. Velocity control my way. And I'll take both of those. That little thing called power GUI continuous. Well, that's pretty important. All right, torque control small 4-bar. Let's paste this in like this. Kind of get it all set up. Okay. And so instead of directly commanding torque into our mechanics, kind of assuming there's such a thing as a ideal torque generator, well, it's kind of recognized if you choose a motor properly, they can be that, right? We understand them really well, and we're really good at controlling them, right? And so our mechanics set it up so that I have a calculation of theta right there, and I got angular velocity right there, right? And I think I got it. Let's go ahead and hit run. Those both look pretty good. Let's see if I can get that in. Yeah, here's the animation. So that looks really good. Should have shown this before. I think, well, what we're doing here, again, we're comparing commanded motion with delivered motion. So obviously we're doing really well, even with the AC motor in there. And that the error is on the order of like 10 to the minus 4 degrees. I think without the motor, I think it was like 10 to the minus 5. All right, so okay. What I think's real cool to look at, though, because we saw them before. We saw those nice sinusoids. Okay, and what I think we're about to observe is, again, how well this field-oriented control approach really works, how adaptive it is, and it doesn't necessarily need to be a constant inertia shaft, and it doesn't necessarily need to be, sinusoids, so it could be 120 degrees out of phase. And this one, we kind of look at it and we go, oh wow, it's carrying current at the end. The one circuit's going to be 0.4 amps, and the other ones are going to be, looks like 0.2 amps. And I'll go to this guy. And again, I think I mentioned it earlier. It finishes in a position where gravity is acting on it, and it needs to carry a torque to hold that final position. So, right. And so this last piece we're going to kind of get into right now is the fact that there's a number of ways to interpret this. But it's really the fact that we have an inductor in circuit, and it's a real big inductor, right? And that's because the motor that we've worked with our initial example had like a stall torque of like 700 or something like that. So quite a bit of winding. So think of windings creates a lot of torque, but also creates a lot of inductance. And so the idea that we're giving ultimately discontinuous torque, well, that's a little bit of an issue. And definitely there are these videos I did where torque is basically what's called J times alpha in a way. Again, because of mechanical linkage that is nonlinear, things change quite a bit. But it's this idea that, well, if you got a motor, and because currents can be on that next derivative, you actually want your transitions to be even more smooth, and that's where you get into these things where people talk about finite jerk. They'll talk about past jerk. It's snap. Then so snap is the second derivative of acceleration. The first derivative of jerk. Jerk is first derivative of acceleration, and so forth. But there's this kind of progression that's position, velocity, acceleration, jerk, snap, and the next two I think is really cute or funny if you liked eating Rice Krispies in the 1970s, which is snap, crackle, and pop. Okay, but anyways, I usually I stop at acceleration, but sometimes I go to finite snap. Okay, anyways, but because this motor is so big, right, and so we're going to make it a little bit smaller right now. We see that our requirements here less than a Newton meter, and speed is about 2.5 radians per second. So let's reduce this to 10 Newton meters. What do we have? 1 Newton meter and 10 radians per second. And again, this is what you'd find in a motor manual somewhere. So I'm going to make it 1e minus 5. And I'll even do this thing called pole pairs. And I'll just say that if you open up a real motor, you're not going to see just 3 windings. You're going to see probably 12. And why 12 is because there's 4 pole pairs. And again, why they call them pole pairs, it's a little bit of a mystery for me. Don't know why I misspelled pairs also, but let's just kind of go with it right now. And maybe this time we'll watch it from this screen. Show the whole thing. This is where we were before. Right. Again, we got more pole pairs, and you'll see that there's kind of a recycling of the calculation that takes place each time you go through a quadrant. And so a quadrant, why is it a quadrant? Because there are 4 pole pairs, right? And so that's what your voltage and current now look like. And of course, speed and torque will be the same, and accuracy is still beautiful. So anyways, that's kind of why I wanted to present. I think yesterday it took me about 2 hours to present all this stuff and had to work through a few confusing issues. I think this one was a little bit more organized, and I think it's kind of a nice way of packaging some content that really does fit together. Usually I like to do videos that are like 10 minutes or less, and this one, I guess we're right around an hour and a half. So anyways, thank you for watching, and let me know what you think. I love it when I get comments. All right, talk to you later. Okay, bye. Hi, it's Terry Dennery of the MathWorks. So this is an appendix. So I recorded that, the first part of this video, I think it was last Friday, and I was very pleased with it. I hope you are too, and I appreciate you making it to here. So maybe that implies a little bit that you did like it. But there were a couple of errors, and certainly having that little overshoot even when I applied the feedforward control. These were a few things that kind of bothered me. I kind of thought about over the weekend, and I spent a little bit of time this morning just kind of figuring out some of those issues. So, and I watched the video too, and I certainly saw this error that I'm going to address first. So this was probably, I'd say, in the maybe the second half hour of the video, where I put together this horizontal bar linkage. Let's go ahead and run the model. And it goes up 30 degrees, and it looks decent. And we looked at this. You might recall this from the earlier part of the video. I even kind of zoomed in. Let's click on that guy right here, and you saw that little oscillation going on. And it's, yeah, it's not bad. Okay, maybe that's as good as we'll do, right? You know, as soon as I started watching it, and I kept on seeing, oh, I'm feeding back angle into what's supposed to be a W rads per second. I'm going, oh, come on, Terry, it's right there. It's right there. Let's fix this. And so obviously that's wrong, right? And so, you know, that this really represents, well, this is your DC motor connected to a lever bar. You know, it actually is a misrepresentation of the physics. You know, so please excuse me for that. I'll try to do better next time. Okay, so let's just delete this. All right, and what I'm doing now is let's just kind of go get the true angular velocity. I'll just call it W. Right, and let's divide by S there because it's radians per second. Okay, and with that, we got the right thing, the appropriate thing that will essentially drive the back EMF voltage, which is part of the calculation taking place there. And we'll just see how we do now. And so very, very different. We get rid of all that crazy oscillation at the beginning, and we ultimately do kind of settle in. You might recall from the previous part of the video that we did saturate our controller, but I'd say it's probably a good idea to retune it. These were the values for the misrepresentation of the DC motor that we had earlier. And the solid lines, the new answer, represented by these parameters right here. And I'm just going to go with that. So I'll update the block with that. Close this. Click on OK. And I think I'll watch, because we retuned it to kind of get rid of it. So you'll have to use your memory a little bit here. But I'd say that looks a lot better. All right. And it is saturated voltage, and so I guess that is a somewhat achievable thing with an overshoot of about 12 degrees. Is it 12 degrees? No, 12. Yeah, we did switch to degrees, and it is position control. Yeah, so that's where we are now. All right. Okay, and well, I won't make the, I think, if you got into here, you saw me talk about this like in the last 30 minutes. So I'm going to just say, okay, now I feel a little bit better about that model, that one's correct. All right. And then the second one is one where you might have even saw it in my face as I was watching. I was going, ooh, why is that one still got an overshoot? All right. So here we are here. Okay. Now recall this one was built from scratch. Every one of these blocks is pulled in and captured in that video. And you hit run, run it. Certainly doesn't look that bad. You might have even seen it in that animation that there's a little bit of an overshoot. Right. And you certainly can see it right here. Okay, and it's not a whole lot, less than 1/10 of a degree, right? But it gets much more apparent when we do this. And we go 0.05 seconds to do that transition. And we hit run. And you get a big old overshoot then. Yeah, it's not horrible, but it's about 3 or 4 degrees. All right, so a couple of things here. All right, and it's first of all, we got our inner loop and our outer loop. Okay, so here's kind of the idea that we got a perfect torque delivery system. And so we're going to just bypass that motor and we're going to just plug in right there. And if I hit run, beautiful. Okay, so we know our outer loop is really good, and our outer loop knows how to calculate the torque that will lead to something that is really, really close to a step function. But again, if you zoom in, it's not a step function. It's just a very, very rapid transition. And for that reason, we've controlled the angular acceleration so that it doesn't really make that impossible request of infinity. It's really, just asking for something pretty fast as measured by this transition time right there. Okay, so that's good. All right, and so what that tells us is, well, we got a little bit of a problem with our motor. Right, and so here's where I then found a couple of problems. All right, and so, and I think I will move it back because it might be easier to see it this way for a transition time. Notice that this was being blocked by me a little bit in the video. So let's make it 0.5. All right. And you'll see I put the, oh, actually I didn't. Let's see, let's put the scopes that I want in here. Well, here's what I do want. I want that torque as calculated by the outer loop, the mechanical control loop. I want it to be compared with what we are going to get here. Okay, and so you can see that the issue we're running into is an inability to kind of deliver on that torque right there. But we also got this kind of crazy thing at the beginning, and I decided, we got to deal with that. That's definitely an issue, right? And when I first saw it, I go, okay, that might be something I want to kind of deal with, only that it's going to allow my integrator control, part of the PID, to accumulate error that really shouldn't be there. And what we have here is an initialization issue. And in a way, you might say that the premise of what we're doing here, which is we start off horizontal with a motor that is off, well, that motor can never actually hold a horizontal position if that shaft is really unconstrained from being affected by gravity. If we put in some sort of lock and stopped it and all that kind of stuff, then maybe so. All right, and so I decided, well, let's just kind of get it to an initialization that actually requires zero torque, right? And so that initialization would be starting off at minus 90 degrees. Initializations always make me a little nervous. It's like, do I know the reference correctly? It's that kind of stuff. But anyways, we got to initialize both the mechanism as well as kind of change our commanded motion. And so here we need to get to the revolute joint. And so this is targeting now, which, this is a little bit of a thing to explain perhaps at some time. But, target, they use terminology like this with the tool SimScape multi-body because sometimes an initialization of one joint might actually impose an initialization on other joints, and things can conflict. All right, and that's why they use that term target. But for the most part, this is a simple system, and it's clear that that's not affecting anything else. Anyways, let's just go ahead and so we get that. I think that will work. So we're going to basically go this time from minus 90 to 30. Let's watch it from here. All right. So if I did everything right, that should start off pointing downwards. So let's hit the green button. And all that looked really quite good. And we come in here and we see that we still got a little bit of that overshoot. Right. So this is where things got a little more interesting for me. Right, and so I'll just say that I tried all the checks, and I checked and made sure. Well, you can kind of see it. See here, torque. Okay, maximum torque is nowhere close to the stall torque, so that's good. And this was a little bit of a pain, but I'll do it anyways. Let's come here. Let's get the velocity as defined there, which is in degrees per second. And with that gain, we're going to map it in radians per second. And I'll hit run. And you'll see that we're maxing out at about, looks like maybe 7 radians per second. Okay, so anyways, that was, what do they call that? Oh, whatever. It didn't matter. That was not the issue, right? So then I started thinking about, well, motor operationally should be able to hit the torque and speed that we need it to. Perhaps it's not being controlled properly. Right. And so that's what we had. Right. And what I wanted to show is the torque comparison. Right. Yellow is what's commanded, blue is what we got. So we absolutely can see that there are some issues there. And so then I thought, well, let's just retune it. And you know, it's interesting. I kind of brought that up in the video. I noticed, which is it's all I. And I kind of like that it's all I, because I is actually kind of a much easier thing to calculate than a D, for example. And so I think it's implementable, right? And so tuned response and block response. Well, that's a little bit, I'd say, misleading to say that that's kind of my tuning. You know, it all comes down to your requirements, and you know, there's some general optimization that probably meets a reasonable set of standards that's been kind of governing this automatic tuning. But for what we're really asking of this now, it needs to be way, way faster. And so I'm going to just kind of keep on clicking on this. Actually, I should keep on showing this as I do this. You know, and you're going to see that it just keeps on increasing my gain on I. And P and D are both 0. All right, so let's update with that. All right, and let's look at it right here. Let's hit the run button. All right, and at least for 0.5, you're going to see we're getting really quite close. And I would say that that overshoot might still exist, but it's very diminished right now. And so anyways, that's for our slower transition. And so now let's make it really fast. And so it'll be 0.05 seconds. Right. We'll hit run. And so we're still getting that overshoot. And so again, this will kind of come down to what your requirements, and perhaps there's an issue with kind of the tuning that I'm going to do. But again, I like iGain because iGain is, you know, integral. You know, it's kind of the idea that it's a little bit tricky to take the derivative of a discrete, you know, signal, meaning that you only get a point every whatever sample time. But integration works much, much better. It's just like, you know, area under the curve, kind of Runge-Kutta type of numerical integration. And then the other thing that's kind of going on here is, well, you know, it's all I, and in a way I don't even really need to jump into the optimizer or the tuner again. And what I did find was about 10 times this, which would be a little bit over 2,000. I'll make it 20,000. And I'll hit run. And it's almost 0 now. Right. And again, we could probably make it even bigger, but I'll say I'm kind of happy with it right there. And so the conclusion that I was really kind of going for as I put this whole presentation together was, you know, what you know matters. You know, what you know will be incredibly useful for you in controlling such systems. And maybe here's a good way to kind of wrap it up. I kind of like this idea, right? And this goes back, at least the way I'm going to say it, to a really good customer meeting I had a few years ago, right? And so I was working with a real good controls engineer, and he basically told me, if I'm really doing my job, if I'm really doing my job right, it's like my PIDs do nothing. Okay, and let's magnify that so we can really see it. Let's also just kind of zoom in on kind of where things are really happening. All right. Okay, and so what we got here in yellow, you can see that because it's going into the scope right here. That's the contribution of that calculation. You're going to see they're just summed up, added up directly. That's coming from your feed forward piece, right? And this is what's coming from your PID or your feedback, right? And I think the correct way to say it is, if I'm really doing my job correctly, it's like my PIDs almost do nothing, right? And what they're really doing here is doing what they do really well, which is they make error go to zero, right? And so the feed forward's great, but as soon as things kind of go off, where your presumption, and our presumptions coming from the fact that we know what we were commanding it to do, as soon as that's not what's really going on with the real linkage, then all bets are off, and what you might be doing through feedforward might be more destabilizing than stabilizing. Okay, and that the job of the PID, I think of it almost like a rubber band. It's sort of like to hold together what the real physical system is doing compared to what your model, your anticipation of what it will be doing. But it holds it together, right? And every time it begins to depart, it essentially applies the restoring force that keeps them synchronized. Okay, so anyways, with that, I feel pretty good that we kind of covered the material that supports that conclusion quite well. Certainly, I think what I'm showing you is a real professional way for designing control algorithms for real systems. And we certainly focused on the mechanical piece in kind of supplementing the overall presentation. But this works for anything that you might control. It would work for your air conditioner. So anyways, thank you. Okay, bye.